question once again. So the 5 capacitors are connected in this way, and so the values of C1 and C3, C2 and C4 are same. Therefore, we get equivalent circuit like this. Okay, so here it reduces to a Wheatstone's network. The current through the capacitor C5 will be 0. Therefore, no charge will flow through this, and therefore we can reduce the network into 2 series capacitors branches connected in parallel. So first we calculate the series equivalent of the 2 branches and then the parallel equivalent. Yeah, so you can do the calculations here your own. So please do the calculations. Okay, so C1 and C2 are in series, therefore equivalent capacitance will be 3 microfarad. Again, another branch also 3 microfarad. Then 3 microfarads are in parallel. Then the equivalent capacitance will be 6 microfarad. Okay, so the correct option is C. So if you want, just go back once to the options. Yeah, see here, 6 microfarad. I hope you all can see. So that is the correct option. Okay, so hope you are all noting down. Okay, so we'll continue with the next question. See, 4 capacitors, each of 25 millifarad, are connected as shown in the figure. The DC voltmeter reads 200 volts. So the charge on each plate of the capacitor is. So here, okay, so there is a, see the connection is there between this. Okay, so the circuit will be like 4 capacitors, one below the other in parallel. So this portion we can bring it back to this side. Here only you will get the, see the 2 capacitors will come like this here only. Okay, so we can have 4 capacitors. Okay, so then charge on each plate of each capacitor will be same, right? So all the charges will be same, right? So Q is equal to C into V because they are same value. All capacitors are having same capacitance and connected to the same voltage. Therefore, charges on each plates will be same, but they are polarities like there is no actually the polarity, but they have given like plus or minus, plus or minus. So the answer also they have given the plus or minus symbol. So C into V will be now 25 into, yeah, so it is minus 6. Again, it is micro, okay, into 200. So 25 into 200, you will get 50 or 5000 into 10 to the power of minus 6 will be 5 into 10 to the power of minus 3. So what is the correct option? See, the correct option is here, 5 into 10 power minus 3. So it is B actually. Okay, correct option is B. Okay, so hope you are noting down. Some corrections are there, please make it. This is micro, and the option, correct option is plus or minus 5 into 10 power minus 3. Correct option is B. Okay, so I will move on to the next question. Yes. So it's a bit lengthy. Please read the question, students. So a charge plus Q is fixed at each points x equal to x naught, 3x naught, phi x naught and so on up to infinity on x-axis, and charge minus q is fixed on each of the points 2x naught, 4x naught, 6x naught up to infinity. Here x naught is a positive constant, means towards the positive x-axis, and then take the potential at a point due to a charge q at the distance r from it to be q by 4 pi epsilon naught r. Okay, then the potential at the origin due to the above system of charges. So you have to calculate the potential at the origin due to the system of charges. So now here you can see that the charges plus q and minus q are placed, like if you have a x-axis like this, you have points 1x naught, 2x naught, 3x naught, 4, 5, like that. You have alternate positive and negative charges. Like if I take potential at this point as V1 and this point as V2 and V3, V4, like that, at every odd number points you have a positive potential, and every even numbered points you have a negative potential due to minus q charge. So now what is the net potential at the origin? So we'll see the solution step by step. Potential at the origin will be, due to all positive charges, it is V1 plus V3 plus V5 and so on up to infinity, minus due to all the minus q negative charges, V2, V4, V6, sum of all of them, okay, up to infinity. So then the next step, so here you can take this as q by 4 pi epsilon naught 1 by x naught minus 2 by 1 by 2x naught plus 1 by 3x naught minus 1 by 4 plus 1 by 5, like that you will have up to infinity. Again here x naught also I can take out, then you will get 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, like this. So what is this? This is again an infinite, standard infinite series. Okay, that is nothing but, it reduces to, it is nothing but log 2 series, log to the base e 1 plus 1. This you come across just in one of the previous problems. I just explained that, right? So infinite, standard infinite series, so log e of 1 plus 1. So that is nothing but q by 4 pi epsilon naught into x naught log to the base e2. So here q log 2 4 pi epsilon naught x naught is the option D. Okay. Hope you have understood this. So note down these steps, students. Okay, so I'll move on to the next question. Question number 22. So read the question, students. Two spherical conductors A and B of radii small a and small b, where b is greater than a, are placed concentrically in air. The two are connected by a copper wire as shown in the figure. So I'll show the next diagram. Okay. Yeah. See, this is the diagram. So one spherical conductor of radius small a, another spherical conductor of radius small b, such that b is greater than a, and these two are connected by a copper wire. Okay. Then the equivalent capacitance of the system. Here you may get an impression that it is a spherical capacitor or like this, so this may be the answer like that. But here this is the point to be noted. Here these two are connected. This is not an dielectric medium or insulating medium in between the spheres. Okay, so this is not the spherical capacitor's case. This is a charged sphere. Like the small value of A, if you can just neglect, then there is actually a standard formula for this, that I think just in the synopsis we have explained this. So see here what happens, all the charges given to the inner sphere will pass on to the outer sphere. So the capacitance of the outer one will be the capacitance due to a charged sphere. Okay, so capacitance of a charged sphere is 4 pi epsilon naught r. Okay, so you got that in the synopsis part, 4 pi epsilon naught r, capital R, that is the radius of the sphere on the surface, for the surface charge. Now here that is the radius is nothing but b in this case. Therefore 4 pi epsilon naught b is the correct option. Okay, so here the thing is, you should not tick this option thinking it as a spherical capacitor. Here there is a connection between the two spheres, therefore it is like a charged sphere, completely charged sphere. Okay, so this is the option C. So note down the answer. Yeah, so I'll move on to the next question. So read the question first. A hollow metal sphere of radius 5 cm is charged such that potential on its surface is 10 volts. Now the potential at a distance 2 cm from the center of the sphere. So now it is a C. Understand the question properly. Hollow metal sphere of radius 5 cm. Okay. So the potential is asked at a distance 2 cm from the sphere, means this point comes where it is inside the sphere, right? So can you tell me what could be the answer? Okay, see what is the, yes, some of you have guessed I think correctly. Potential at any point inside the sphere is equal to the potential at the surface of the sphere. So because the point is given 2 cm inside the sphere, so it is same as the potential outside on the surface of the sphere. So that is the correct option, option B. So that is the 10 volts, same. 10 volts is the correct answer. Okay, hope you have noted it. So I'll move on to the next question. Yeah, so read the question. On decreasing the distance between the plates of a parallel plate capacitor, its capacitance. So here also you must be able to tell me the answer.
Increases.
What is the formula? Decreasing the distance. Yes. So what is the formula? C equal to epsilon naught A by D. So D is there in the denominator. So yes, capacitance D decreases, capacitance increases. Okay. So D as D decreases. So decreasing the distance, right? So D is decreasing. So the capacitance will be increasing. Okay. So that is the correct option. Okay, so option D. So decreasing the distance, capacitance increases because C is inversely proportional to D. Okay, so hope you have understood that. Okay, I'll continue. Question number 25. Read the question. A charge is brought from a point on the equatorial plane of a dipole to its midpoint, midpoint, full stop. Which of the following quantities remains constant? So charge is brought in an equatorial plane of a dipole. Okay. So in the equatorial plane of a dipole, that is nothing but, so the two charges, dipole is the equatorial plane if you consider. So in the equatorial plane of the dipole, what is this? This is nothing but an equipotential surface, because it is at the same distance, right? Constant distance between the two charges, right? So therefore this is a equipotential surface. Therefore what remains constant here? Potential remains constant. So here the option D, electric potential remains constant. See, that is the correct option, option D. Okay, so you are noted the answers, right? So I'll continue. Okay, so question number 26. So this is again the direct question. Energy stored in a condenser of capacity C, which has been raised to a potential V, is, yes, you all know this. Okay, so this is nothing but half CV square. So this is the option B. Okay, so half CV square. Correct option is B. Okay. Next, I'll move on to the next question. Question number 27. So read the question. So two equally charged spheres of radii A and B are connected together. What will be the ratio of electric field intensity on their surfaces? Yeah, see the options are like this. Okay, so this is the diagram. Two equally charged spheres of radii A and B are connected together. Okay, now what will be the ratio of electric field intensity on the surfaces? So charge on each capacitor, we can charged spheres, we consider it as to be Q. They are connected together. Okay, therefore their potentials will be equal. The potential VA equal to VB. Potential is VA equal to VB. So now you take one charge as Q1. The other one will be 2Q minus Q1. Okay, A charge on A is Q1. Charge on B will be 2Q minus Q1. Or here actually you can take Q1, Q2, directly Q1, Q2 also you can take. Need not consider this. Okay, take this as Q1, here it is Q2 only. Now you equate the two equations, 1 by 4 pi epsilon naught Q1 by A equal to 1 by 4 pi epsilon naught. So instead of this you can just take Q2, okay, Q2 by B. So that is equal to now Q1 by Q2. So what happens in this case? 1 by 4 pi epsilon naught on both sides is common, so cancels out. So Q1 by A equal to Q2 by B, or Q1 by Q2 is equal to A by B. Okay. Next, what you have to calculate is the ratio of the electric field, right? So take the formula of electric field for both the conductors A and B, EA by EB, 1 by 4 pi epsilon naught Q1 by A square divided by 1 by 4 pi epsilon naught Q2 by B square. Again this is Q1 by Q2, okay, into B square by A square. Now Q1 by Q2 you have already calculated as A by B. Substitute A by B into B square by A square, that is equal to B by A. So ratio is B is to A, or B by A. So that is the correct option, option C. Okay. So there are some corrections here. Please note down, students. This point you can either take it or you can directly take Q1, Q2 also in this. Okay. Need not consider once Q1, 2Q minus Q1. Again, you are getting the same thing there. So you can take it as it is. So please note down the steps, students. So the point here is the potential on the two charged spheres is same. So you equate it, get the ratio of charges, that we will substitute in the ratio of the fields. So then you will get the relation between the radii of the two charged spheres A and B, that is as B by A. Okay, hope you have understood this. So I'll continue the next question. So, question number 28. Yeah. So a given charge is situated at a certain distance from an electric dipole. Okay. In the end-on position experiences a force F. Now, if the distance of the charge is doubled, the force acting on the charge will be. So you just read the question and get the formula. Okay. So force on the charge, that is the F is equal to Q into E. Okay. Now Q into E is C. K, that is 1 by 4 pi epsilon naught 2p by r cube, which is this. This is the charge, the electric field at a distance from a electric dipole, right? So field on the axis of an electric dipole, that formula K into, that is 1 by 4 pi epsilon naught 2p by r cube. Okay, so you got, hope you got it. Then force on, in this case, will be Q into E. So Q into K 2p by r cube. Therefore, now force is proportional to 1 by r cube. Okay. So now what is this r? This is the distance, right? So what is given in the sum? The distance is doubled. Means r is made 2r. What will happen? 2 cube. Right. 2 cube is 8, right? So what will happen to the force now? Force will be, so when r is doubled, force will become 1 by 8 times, okay, of F. So new force, the new case will become equal to F by 8 or 1 by 8 times F. So that is the correct option, option D. Okay. So if you want me to explain once again, force on the charge F, on force on the charge Q, situated at a distance R at a on a dipole, axis of a dipole. So field on the axis of a dipole, that formula you have to consider. So how we get R cube here? Using this formula, electric field on the axis of a dipole. So by that you get F proportional to R cube. Therefore F is 1 by 8 times F. New F is equal to 1 by 8 times F. So that is the correct option. Students, please note down the answer. Okay, so we'll move on to the next question. Yeah, so please read the question. 8 drops of mercury of equal radii possessing equal charges combine to form a big drop. Then the capacitance of the bigger drop compared to each individual small drops. So here, this is like a recasting type of questions which you used to get in mathematics in your lower classes, right? What happens when a object, a smaller object, more than one smaller objects combine together to form a bigger object? Volume remains constant, right? In the two cases, the volume of the two cases will remain constant. So same thing we will be using here. See, the volume of 8 small drops is equal to volume of a big drop. Okay, so take the volume. Now what is this? It is sphere, right? The drops are in the shape of a sphere. So 8 into 8 small drops, 4 by 3 pi r cube is equal to 4 by 3 pi r cube. Single drop, volume of the big drop. Okay, so R is equal to that. In that case, the R will be equal to 2R. So small r, it is capital 1 is capital R and another is the smaller R capital for the big drop and r is small r for the smaller drop. Okay, so now as the capacity is proportional to r. Okay, what is r here? That is the radius of the sphere, right? So the capacity is proportional to r, right? So hence the capacitance becomes how many times? 2 times. So the capacitance becomes 2 times. So the capacitance of the bigger drop compared to the each individual smaller drops will be 2 times because r is equal to 2r. Okay, and capacity is proportional to the radius of the sphere. Hope you understood this. So option C, please note down. So we'll move on to the next question. So please read the question and the options, students. So I'll try to finish it off. A parallel plate capacitor. Okay, a parallel plate capacitor. So 10 minutes left. So we'll continue. A parallel plate capacitor is charged by connecting it to a battery. Now the distance between the plates of the capacitor is increased. Now in this case, which of the following remains constant? So see, as the capacitor remains connected to the battery. So here capacitance, when the plates, distance between the plates increased. So you know the formula, C is equal to epsilon naught A by D. So capacitance will change. Charge on each place, again charge is equal related to capacitance and it will change. Energy stored again depends on C, it will change. So it is now the capacitor is connected to a battery of a fixed potential. Therefore, the potential difference provided by the battery remains constant. Okay, so the option C, potential difference between the plates of the capacitor remains constant. So capacitance will not remain constant. Charge as well as the energy stored will not remain constant. They will vary, but the potential difference between the plates of the capacitor will remain constant because it is connected to a battery. Okay. So note down the options, students. Correct option C. Okay, so we'll move on to the next question. Yeah. So read the question. So two vertical metal plates carrying equal and opposite charges kept parallel to each other. Okay, a small spherical metallic ball is suspended. So I'll show you the diagram. Okay, yeah, so that is the diagram. Here two plates are there. In between a spherical metallic ball is suspended. Okay, then the ball is hanging freely between at the center of the two metallic plates. Now the ball which is uncharged first is taken slowly towards the positively charged plate and it is made to touch it. Okay, so then what will happen to the ball? See, read the options one by one. Stick to the positively charged plate. Whether it will stick? No. It will come back to its original position and will remain there. Whether it will remain there? So oscillate between the two plates. No, it will not remain there because it is now getting charged, right? So that will get repelled. Okay. Now it will move towards the other plate. And what will happen? It will touch the other plate because the other plate is charged negative. Now this is a positive charge. It will attract, right? So when the ball touches the another plate, it will get negatively charged. Then again it will get repelled. So because of that, again it will start moving in the opposite direction, then get attracted towards the another plate. Again it will move and touch the plate. Then again it will come back. So what will happen? It will remain oscillating at the extreme positions, touching the plates. Okay. So now what are the options? C and D oscillates between the two plates, touching each plate without touching each plate. So which one is the correct option here? In this case, C. Okay, so hope you have understood that. So the bob keeps on oscillating between the two plates, touching it. Okay, so please note down the options and the correct option. Okay, so I'll continue. Few more questions are remaining. Okay. Okay, so few more questions. A conducting sphere of radius r is given a charge q. So the electric potential and the electric field at the center of the sphere. Again, see, again, you know all the formulas, all the synopsis you have studied. This is again the direct question. We should see what is the electric potential of a conducting sphere, okay, at the center, and the electric field. Okay, so you know that conducting sphere at the center, electric field is 0. Okay, and the electric potential is given by the formula Q by 4 pi epsilon naught R. Right? So now which is first given there? See, which is 0 and this 0, which is the correct option here? Here it is R square is there, so that is not the option. Here too, both are not 0, both are not 0, so this is not the option. Both are 0, that is also not the option. So this is the correct option. Q by 4 pi epsilon naught, that is the first one. Electric potential and electric field, that is 0, that is the second one. So